Okay, so we're on day 6. We got the last page to do. We'll see if we do all of it. Before we flip the page over, we wrote down this formula for the triangle, or the Pythagoras formula, and it was used to find the side C. Oops, come on. Which is the longest side of the triangle. However, sometimes you're asked to find one of the shorter legs. And we manipulate this formula. Do you remember how that formula looks like if you're asked to find side A or B versus?
Squared minus the other.
Yeah. So you go your longest side squared minus whatever other side you're given. So let's just say you're given B squared. That equals one of your shorter sides. Right? So to get the longest side, you add the two squares. Then you take the square root. To find the shorter side, you subtract the two squares. Then you take the square root. Right? All right. Let's go into the back side. All right. So this question here, you're asked to find how much space is in these little shaded corners. Right? And this is a very stereotypical question. You saw something similar in grade 8, you're seeing it in grade 9, and you will see it in grade 10.
Are they 4 centimeters each?
Right? So, no, we'll figure it out. So we're asked to find area, right? So that gives us a hint of what kind of formulas we want to use. We want to use area formulas, okay? And we don't have a formula for this little shape that looks like this. It's not a triangle, it's like a little curved thing here, right? So we don't have a formula for that. So what we need to do is use some of the formulas we already have and try to figure out what those little corner pieces might be. Do you see any strategy we could use? Blake?
Calculate the area of the square.
Yep.
Calculate the area of the circle, and then subtract the area of the square to the circle.
Yeah. So Blake is saying, hey, let's figure out how big this is. We subtract this. Well, let's do circle. And we'll get whatever is left over is the little mini pieces on the corner. And I know lots of people have difficulty visualizing, so this morning I quickly cut this thing out. So this is our shape, right? And if you figure out how big this is and you take out the circle, that's what subtraction means, you're just left with the stuff on the sides, right? And that's what we're trying to calculate. That's what Blake translated, right? He's left with the side pieces. Not the best cut out, but sort of hopefully give you the ideas, right? Okay, so we need to figure out how big the square is, how big the circle is. So the square formula, area of a square, so I'm going to use shorthand, A for area, a little box for circle, square. Grade 8 formula was W times W. In grade 9, we're going to do W squared. So in order to use this formula, we need to know what W is, the length of the side. How big is the side? 16 centimeters. That's given right here. So where we see W, we put in 16. Here's the little 2. There we go, 16 squared. We grab a calculator for that. That's a big number. 16 to the exponent 2, and we get 256. And areas always have units. What should the unit here be?
Centimeters squared.
Centimeter squared. Okay. So job 1 done. Found the square. Job 2, find the circle. So area of a circle now, that's in red, is equal to pi, which is 3.14 times r squared. So we need to know what r is to use this formula. What is r? Blake?
8.
8.
Half
Okay.
of 16.
Half of 16. Remember, r is distance from the middle out. If all the way across is 16, halfway across must be 8. So we plug in 8. 3.14 times 8 squared Now this becomes a BEDMAS question. I see two math operations. I see a multiplication and I see an exponent. Which one do we do first?
Exponent.
Exponent. So we got to do this calculation first. So 8 squared is 64. And you still have the 3.14. And you go 3.14 times 64. And we get 200.96. Then we use Blake's strategy. We know how big each one is. We just subtract the two to get the little tidbits on the side. So area of, let's say, corners is equal to 256 minus 200.96. All right, so I grab my calculator. I got 256 minus 200.96, and I get 55.04, and that's centimeters squared. Now, typically with these kind of questions, it will say a rounding rule. And this question says, give your answer to 1 decimal place. And how would our answer look like if it's 1 decimal place? Damien?
Just 55.
Not just 55. Christian?
55.0.
55.0. We need to show that decimal place, even if it's 0. Right? So, with word problems, just give a little statement. The shaded area is 55.0 centimeters squared. Okay? So there'll be a question almost identical to this in your assignment, right? So you find the two shapes, you subtract them. Okay. Next one. Now, I personally find a question like this probably one of the easiest questions I can give you, but students tend to make the most number of mistakes because they kind of get flustered and lost and don't know what to do. And this is a question probably directly out of Science 10 you'll be doing next year. The path that a skydiver follows the following formula. D is equal to 4.9 t squared, where D is the total distance in meters, t is time in seconds, and calculate the distance the diver falls in the following times. So lots of stuff going on. So when you're given a question like this, they are going to give you an equation. That's here. Right? That's what you're going to be using. Then they're also, in some way, shape, or form, going to tell you what each letter in that equation stands for. Right? So here they told you D is distance and T is time. Then they're going to give you one piece of information and ask to find the other one. So in here, they say the time is 2 seconds. Find distance. So we use that equation. So you write it out. Distance is equal to 4.9 t squared, or whatever equation that they may give you. And all you do is replace the letter with its value, like we did in, I think, unit lesson 4, I want to say. So here, they're saying the times value is 2. So where we see t, because t stands for time, we stick in the number 2, right? And I gave you the tip of putting in brackets, because that sort of sometimes helps see the calculation a little bit better. So wherever we see the t, we stick in 2. At the end, we get the value of d, right? So here, I see two math operations. Well, I see a multiplication and exponent. Do you see both of those?
Yes.
Right? A number touching a bracket or a number touching a letter means to multiply. If you don't see it, you can put a little x in there to help you out. Right? And a square. So what do we do first? Blake?
Exponent.
The exponent. So we're going to do this first. And we go 2 to the exponent 2. That is 4. And we keep everything else the same. Then we go 4.9 times 4. We figure that out. 2 times 4. And the answer is 19.6. Okay, 19.6. Now this is a measurement because we're calculating distance. What should the measurement be? Is it centimeters, meters, kilometers? That information is given to you in the question, right? Meters. So this right here, distance is measured in meters. So a lot of unpacking to do with these kind of questions. Okay, so now the exact same question. They say, hey, do it for 4 seconds. So try again. This is on you. Grab your calculator out, plug in 4 seconds, see if you come up with the right answer, right? I'll pause for a second. All I'm going to do is write up the final answer. 1. All right. Okay, so I don't think we'll do the question on the right-hand side. We'll do this one. Now, this is a very practical application. Christian, no. Okay. Now, so the question goes, a type of bacterium is known to triple every hour. There are 50 bacteria to start with. How many bacteria will there be after each given amount of time? So 3, 5, and undetermined. So now, lots of things in life, when they reproduce, they follow an exponential path. So if you were to graph it, it would look like this. And in grade 9, you're going to start to be able to understand how scientists and health professionals can start making estimates of how many COVID cases they think, or how bad the flu season is going to be, right? Because they know how quickly it reproduces and how many case counts you have. So the formula that we can come up with today is a simplified version of what they would be using. In about 1.5 years' time, you'll be able to see the full formula that the health authorities use. So we're going to use this as a starting point to sort of introduce the idea. So here, they say we start off with 50 bacteria. That is at time 0. We have 50 bacteria. Okay? And the question is, hey, how many bacteria will there be after 3 hours? How many bacteria will there be after 5 hours? And when they say n is, can you come up with a formula to do a prediction? All right? So, Abby, you have a clue how to start?
Yeah, 50 times the hours to the power of 3.
Oh, you're getting there. Oh, awesome. I'm glad you see it. Okay, so to begin with, for the people who don't see it, what we can is just go time after 1 hour. How many bacteria would there be?
100.
Not 100. 50. Because they say it triples. So you go 50 times 3 is 150. Right? So, and now I'm going to do this so you can sort of see what the formula is going to come from to go through each one of those steps. Time after 2 hours. How many bacteria do we expect to see? 450. And how did you do that? Christian?
150 times 3.
Yeah. We triple how much we have. We have 150 now. The next hour, it's going to triple. So we go 150, what we had, 150 times 3, which is 450. And time after 3 hours, what do we do?
1,000.
Yeah, so you go 450 times 3. And what number do you have, Damien?
1,350.
And 1,350. So this gives us the answer, but doesn't really help us sort of figure out a generic formula. So what I'm going to do is, at time 2, I'm going to rewrite this calculation. Where did this 150 come from? This 150 came from 50 times 3, the step before, right? Came from 50 times 3. then we did times 3. That's 450, right? Just reworking the calculation, writing it somewhere else, right? And where did this 450 come from? Well, it came from the previous step, which is just this number here, right? So I can rewrite that as the previous step, which is 50 times 3 times 3, and then times another 3. Are you seeing a repeated multiplication start forming here? Right? Do you see, I mentioned the word a coefficient? Right? Do you see a base? Right? So here, what's your base?
3.
3. For this one, right? So base is 3. What we see repeating. What is our exponent? 3, because it repeats 3 times. And the number in front is your coefficient. All times. And if I wanted to write the repeated multiplication in exponent form for time 2, it would look like that. For time 1 hour, it would look like that. Okay. Do you see a connection between what time it is and the formula? What do you see?
That
Blake?
every time, every hour, the exponent increases by 1.
Yeah. So look at this. The at time 1, the exponent's 1. At time 2, the exponent is 2. Time 3, the exponent is 3. So for time 5 hours, if we want to figure out how many bacteria there are, we don't have to go triple. We can use our formula, right? What would the formula for time 5 hours look like? Blake?
50 times 3 squared, or 50 times 3, 5.
5. And we calculate that. We go to our calculator and we go, oh, where is it? There it is. Turn it on. There you go. 3 to the exponent 5 this time. Get this big number, and I'm going to multiply it by 50. And I get 12,150 bacteria. Right? So you could just keep on tripling, but I could say, how many bacteria are there in the 20th hour? And all of a sudden that calculation becomes a pain to do, tripling. Whereas you can use your calculator and put a 20 in there and figure that out. Okay, so now the last part is, can you give me a generic formula? So the generic formula looks like 50 times 3 with a little n, right? So we want to describe this. This calculation gives us the number of bacteria. That's what we're calculating. What does the n stand for?
The time.
Time. So n stands for time. Where did we get the 50? What does the 50 stand for?
Bacteria.
Bacteria at the beginning, right? So the growth patterns can change if you have 50 versus 100, right? So this is this number here is your bacteria at the start. Okay. Then we have this third number, this 3 sitting here. Where does that 3 come from? Blake?
How many times it repeats in the other.
Yeah, how quickly does it reproduce? Right? That's what this number is. Right? How quickly it reproduces. Now, I could change this question to, hey, you have 200 bacteria to begin with. It quadruples every hour. What's the formula? What would you write down? I'll just do it off to the side here. Right? So if I said that you have 200 bacteria to start with, that would be where the green 50 is, right?
200 times 4
Times 4 is a reproduction rate, and n. That's it. Then if I said, hey, use this formula to figure out how many bacteria are there after 100 days, you can make a prediction. And that's sort of what they do at the health units to figure out how many flu cases are there going to be, how many COVID cases are going to be. Except for their formula, we'll have a fraction here, and when you get to grade 11, you'll sort of discuss where that fraction comes from and what it stands for. Right? That's how they do their predictions. And we'll stop right there.